Everyone, I am Indrasish. Today I'll be presenting my paper titled Statistics Aware Low Overhead Training and Rate Implications for RIS-Aided System. This is the outline of our talk. First, we'll give an overview of what are we trying to do here. Then we'll discuss our system model. We'll propose a novel channel estimation scheme for RIS-Aided systems. We'll talk about its mean square error and rate implications. Finally, we'll end our talk with a few key takeaways. Okay. Now, reconfigurable intelligent surface or RIS consists of these passive elements that can induce a phase shift on the incident signal. Now, what we want to do here is we want the signals coming from all these RIS elements to combine coherently at the receiver. Here we take an example of the uplink communication scenario. So user is the transmitter and the AP is the receiver. So to achieve this coherent combination, we need to set up the RIS phases in such a way that it cancels out the phases that has been induced by user to RIS and the RIS to AP channel. And to do that, to perform that, the channel state information of both these two channels are required. Now, you might ask that, is this the only way to do this? No. There are lots of techniques that are flying around the literature. You can categorize them in three different paradigms. First one is instantaneous CSI-based schemes, where you estimate all these cascaded channels and configure the RIS accordingly. Then comes the codebook-based schemes, where RIS configurations come from a predefined codebook, and you select that code word, which gives you the maximum received signal strength. And finally, there's this statistical CSI-based techniques, where you set up the RIS configuration based on long-term channel strength. In this talk, though, we'll focus on instantaneous CSI-based schemes. Why? Because it gives high beamforming gain. If you have n element RIS, you get a beamforming gain in the order of n square, right? But this instantaneous CSI-based schemes comes with its own problem, and that is its large training overhead. So if you have n RIS elements, then you might have to send n pilots in order to estimate the n cascaded channels. And if you have a limited coherence time, then that might create problems. All the conventional schemes like on-off scheme or DFT training scheme, uh, they suffer from the same problem. So in literature, many of the overhead reduction techniques are proposed. First kind of techniques is this grouping-based mechanisms, where or grouping-based techniques, where you group the nearby elements and assign a single reflection coefficient for every element in that group. And with this, the training overhead reduces down, but you take a hit on the beamforming. On the other hand, there are some machine learning based techniques as well. Many of them focuses on deep learning based approaches. Many of them focuses on reinforcement learning based approaches. And then there's this reduced subspace least squares based technique. It basically does is it estimates the channel in a lower dimensional subspace, and after estimating it, it kind of reverses it back to the original dimension. In this technique, the number of pilot it sends is equal to the rank of the channel covariance matrix. So there is a significant cut in the training overhead that they achieve. What we want to do here in our work is we want to cut down this overhead even more. And how do you do that? We exploit the spatial correlation of the user to RIS channel to lower the training overhead. Now, why user to RIS channel only? That will come back. We'll come back to it after a few slides. Okay. But first question that should come is why correlation, right? Why you should exploit correlation at all. Now, let us take an example of a isotropic scattering environment in the half plane of the RIS. In such scenarios, the correlation model is a sync correlation model. Now, If you go from one element to the another in both these sides, uh, you can see as the distance increases, there still remains a significant amount of correlation. You can't just, discard it or avoid it. So that's what we don't do. We exploit this correlation, and we propose a novel training scheme, and we derive the optimal pilot powers and RIS configurations for that. We analyze this method's rate implications, and we show that our scheme needs far fewer pilots than several existing schemes in the literature. And this training overhead is not only lower than the total number of RIS elements, but lower than the rank and effective rank of the channel as well. Now, what is this effective rank? This term was proposed, at least in this context, in Demi's paper that is related to RSLS. Uh, so effective rank basically captures the eigenvalues that some the eigenvalues whose sum doesn't exceed a predefined threshold, and this threshold is 1 in a millionth of the trace of the covariance matrix basically. Uh, and what it turns out is this effective rank is basically a quantity that is lesser than rank, huh? And we'll show that our scheme needs far fewer pilot than them. So let us move to our system model now. So we consider a uplink communication scenario where user is communicating with an AP with the aid of an RIS. The user to RIS channel is considered to be non-line of sight and correlated. The covariance matrix of this channel is μhr, where μh is the path loss coefficient, and the corresponding channel from RIS to AP is considered to be a line of sight and deterministic. That's why this channel doesn't come in the key idea section when we say which channels correlation are we exploiting, because it's deterministic, so there's no point. And the direct path between the access point and the user is assumed to be blocked. So we consider a coherence time of tau c, and in this coherence time interval, the first tau time intervals, we send the pilots. Now let us look into the transmission protocol in a elaborate way. So this is our transmission protocol. As I said, tau c is the coherence time, and the first tau intervals, we send the pilots, rest are for data transmission. So for the pilot transmission, we send pilot signals. We consider the pilot signals to be 1 without any loss of generality. And they have the pilot powers to be P1 to P tau, and the corresponding RIS configurations during training are phi1 to phi tau. Okay? And note that unlike the equal power assumption in the literature, we don't put any restrictions on them, on these pilot powers. They need not be equal. They should not have any trains or whatever. Huh? And this RIS configurations also can be anything. They don't come from a predefined set of values like DFT training or codebook schemes. We find them in an intelligent way. That's what we do in this scheme. And with this pilot powers and RIS configurations, we estimate the user to RIS channel, and based on the estimate, we set up the RIS phases and send the data. And data powers are assumed to be equal. Okay. Now, how do we set these pilot powers and RIS configurations during training? That's now the first question we need to answer. We find them in such a way that it minimizes the mean square error in estimating the user to RIS channel for a given pilot power budget. We define this term X, which basically involves the pilot powers, RIS configurations during training, and the RIS to AP channel. Okay. And now we give our optimization problem where we minimize the mean square error in estimating the user to RIS channel, subjected to the pilot power positivity constraint, the pilot power constraint, and the RIS space constraint. To solve this problem, we restate this pilot power constraint. Okay, in terms of x. And this is what it looks like. Now, this problem is non-convex. This is a quadratically constrained quadratic problem. So this is NP hard. We can't solve this kind of problems in a straightforward manner. So we have to find some other ways to do it. And that's what we do. We propose a two-step approach. In the first step, we relax the unit modulus constraint related to the RIS phase shifts. And this relaxed problem has a closed form solution. And this closed form solution comes all the way from a decade back paper in transactions and signal processing. And the optimal solution is in terms of the eigenvectors of the channel covariance matrix. The solution somewhat looks like a water filling kind of thing. You can look into our paper or in the actual paper to get more info about this. For the for the interest of time, we'll move forward. Now you get a closed form solution for this relaxed problem, but ultimately we need to set the RIS phases and the pilot powers. That's what we want. And to get that, we 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 propose a least square split. And this least square split also have two solutions that are the functions of the eigenvectors of the channel covariance matrix. And the expression for optimal pilot power involves this L1 norms of the eigenvectors. And because of this L1 norms, the pilot powers are neither equal and they don't really follow any kind of trend. They are not increasing, they're not decreasing, they really don't follow any sort of trends. And both of these steps have closed form solutions. So complexity wise, this solution is very cheap. Now let us look into some numerical results. First, we will give a numerical results related to the mean square error behavior of our scheme. Then we will move on to our rate implications. Now, for numerical results, we consider a 8x8 square RIS with inter-element spacing being lambda by 8. The coherence interval is considered to be 100 symbol duration. The total pilot power budget for this numerical result is considered to be 40% of the total power budget. And the SNR is defined as the product of the total power budget and the cascaded channel gain normalized by noise variance and coherence time. Now, and for the correlation model, we assume sync correlation model here. In this numerical result, we plot the normalized MSE in estimating the user to RIS channel as a function of the number of pilots for different SNR values. Now, as you send more number of pilots, your estimate becomes better and better and better. So your MSE decreases and finally reaches a floor. And once it reaches a floor, even if you send more number of pilots, it's basically useless. Your MSE is not going to improve, right? And we indicate the point where the floor is reached with this vertical markers. We also plotted the effective rank and the rank. The effective rank of the channel, the channel covariance matrix, turns out to be something around 28. And you can see there is a significant gap between the effective rank and the point where the MSE reaches a floor. And as you decrease your SNR, you can see this gap increases. Basically, what it tells us is if you don't really have the SNR, if you have a low SNR, if you have a low power, you don't need to send more number of pilots. You can send much lesser pilots and be fine with it. Now we looked into this problem in the light of mean square error, right? The whole thing till now. And it says that, okay, you send more pilots and after a certain time, your MSE is going to reach a floor. Even if you send more pilots, it's not going to change. Now we want to look into this problem in a different perspective. And that perspective is achievable rate. we derive this expression for achievable rate. The first term in the expression accounts for the training overhead, and the fractional term inside the expectation and the log is basically effective signal to interference plus noise ratio, the denominator of which accounts for estimation. Okay. Now, as you go on sending more pilots, what basically happens is your effective SINR improves. Your estimate becomes better and better. But after a certain time, your training overhead becomes dominant and tries to pull your rate down. So there is a trade-off between them that really takes place. So we want to capture that trade-off and try to analyze that. That's what we try to do here. But one problem is this expression is not mathematically tractable. And since we are going for some low complexity solution to the whole problem, uh, we try to find a lower bound, which is in terms of the maximum eigenvalue of the error covariance matrix, and we maximize this lower bound instead to determine the optimal number of pilots and the pilot power and data power allocation. So with this, what basically happens is if you just give me the channel statistics, we'll be able to tell you the optimal number of pilots, we'll be able to tell you the pilot power allocation, we'll be able to tell you what should be the data. Everything we can tell. Just you have to give me the statistics. Now, let us look into a numerical result that considers the achievable rate. We take the same setup in this numerical result also, and we show that we show the result for the achievable rate as a function of the number of pilots for different SNR values. And as you go on increasing the number of pilots, the quality of the estimate improves. So your effective SINR goes up, so your rate also goes up. And after a certain point, your training overhead actually becomes dominant and pulls you down. So that's why it first increases, reaches a peak, and then decreases. And the point it reaches a peak is the number of pilots you should send in order to have maximum rate. And those points are marked here with this rate crosses, which is basically the optimum. We have also plotted our bound, where we have shown that our bound tracks the achievable rate quite well, and we also have observed that the optimal pilot length that maximizes its rate is lesser than that required to reach that MSE. Now we claimed a lot of things here, but now we have to put ourselves to the test. How do you perform among the other existing schemes, right? That's what we need to see next. So that's where we benchmark it. Here we optimize the pilot power and data power allocation, and we benchmark our scheme with Gini-aided scheme, RSLS, DFT training scheme with and without grouping. For with grouping case, for each SNR we take a bunch of DFT, a bunch of group sizes, and the group size that gives you the maximum rate is chosen to be the optimal one, and we use that to plot these figures. Now, for Gini-aided scheme, it does better than our scheme because Gini-aided scheme assumes full CSI availability. So there's no training overhead, no estimation error. So it really acts as an upper bound to all the realistic or the practical schemes, to be very honest. For RSLS, it does worse than our scheme, primarily because of two reasons. First reason is they send way more number of pilots than us, because for us, we are going much left. I mean, the number of pilots we send is much smaller than effective time. So that's one reason. And second reason is they take equal power allocation for all the pilots. They really don't optimize it. They don't, talk about the power optimization at all. So that is another reason. As for DFT training, same reasons persist, along with one additional reason, and that additional reason is correlation. DFT training doesn't consider correlation at all. So you're missing the information, and that's why it pays for it. So we have achieved higher rate than the most of the existing instantaneous CSI-based schemes. As for the conclusion, we have proposed a novel training scheme that exploited the channel correlation statistics. We have jointly designed the RIS configurations and pilot powers. We showed that the optimal pilot powers were unequal. We showed that the optimal RIS configurations and the pilot powers during training were the functions of the eigenvectors of the channel covariance matrix. We showed that our scheme has better rate than several existing schemes, with optimal pilot length being smaller than not only the RIS elements, not only the rank of the channel covariance matrix, but also the effective rank of the channel covariance matrix as well. As for the future work, we can extend this work to a multiple antenna system in the base station. We can extend this work to non-LOS model or the non-line of sight model for RIS to FP channel as well. Thank you for listening. Thank you.